introduction, for the invitation to this wonderful workshop. I will discuss unsupervised induction, but basically trying to connect it to our key topic, how do we deal with long tails, and why unsupervised learning with rich, expressive models may be the way to go. So we've had a number of, and first of all, sorry, few people in the audience saw some parts of this talk, right? But bear with me. So we had a number of big successes, I would say, in natural language processing with statistical methods in the last 15, 20 years. However, I believe one of the most important problems where we didn't do so much progress is broad coverage semantic parsing. Predicting semantic representations, and also we want types of representations, and this was coming up in Johan's talk as well, with which we can perform reasoning. So there are many applications which could benefit from semantics. Say information retrieval. Current search systems don't perform any kind of reasoning or very limited kind of reasoning across documents. So they process document by document. But as a motivating example throughout my talk, I will use machine reading. So what is machine reading? So in machine reading, a machine is given a text or maybe a collection of texts and asked questions about this collection. So say we have this very simple text about someone called Lansky. So Lansky traveled to Australia to study at the Royal College of Music, and then he dropped studies and in the end graduated from Trinity. And we have a few questions. And these questions, this example is very simple for humans, but not as simple as we will discuss later for machines. But before going into examples and discussing challenges, I'd like to give you some idea of what I mean in this talk by semantics. And by semantics, here I mean frame semantics. So say a semantic parser is given this text, this sentence as an input, and what it needs to do, it needs to identify key events, key relations appearing in this text. So say you want to predict that there is some education semantic frame, education situation mentioned in this sentence, and the three arguments realized, and they're assigned to three semantic roles. So who is studying, who is the student, semantic role student, it's Lansky, what is the subject, where he studies. And in general, these structures can be quite a bit more complex. So in the same sentence here, we have also a departing situation. Okay, so you can think of this problem as predicting this type of representation, these graphs, but equivalently, essentially, you can think that what frame semantic parser is doing, it takes this text and extract this knowledge in some kind of a database, knowledge base. So semantic frames are very much like tables in this relational database, and roles are attributes. And you will see this analogy will be kind of important in a few moments. That's why I'm mentioning this. Okay, so the outline of the talk is the following. So first of all, I motivate the framework and also explain why I think it's especially relevant for modeling rare phenomena, modeling tail, and then say a few words about framework. So my talk may be a little more technical than the preceding ones, because I will show a specific instantiation of this model and also look a little bit more in details how this works, and then we can have a bit of discussion whether this is really a way to go. Okay, so how do we build semantic parsers nowadays? So what we do typically, we get text annotated by linguists, by experts, and then we use a learning algorithm to estimate parameters of parser, statistical parser, which we then can use to parse new data. But then my argument would be that it's impossible to annotate enough data for semantic parsers to get a general broad coverage semantic parser in this way. And of course, this is especially relevant for more rare phenomena, for the tail, because these data sets won't be large enough to even have examples of this rare phenomena, or we'll have very few examples of them. And just not to stay at extremely high level, let's get back to our example and see what happens when we apply a state-of-the-art parser to this text example we have. So say everything goes well with the first sentence, so he identifies this education frame, so things good. But let's have a look in other two sentences. And so what we see is that this frame semantic parser, which is by the way seen use semaphore, thinks that dropping studies is actually essentially physical movement. So it's like a drop in an object. By the way, if some of you are very familiar with FrameNet, I'm simplifying frame names, so that just not to clutter the image. And essentially the same thing happens here in a question where did Lansky get his diploma. So get is again interpreted as a kind of physical movement. And this is fairly natural, because if you go back and see what you have in a FrameNet data, you don't have that many examples of different ways how you can express graduation or dropping studies. Okay, so that's what we get when we apply supervised parsers. But let's think for a second optimistically. So what would happen if you would actually produce correct representations? And so what is correct? So the ones which linguists think is correct, which correspond to the annotation guidelines, say in this case for the FrameNet. And this is what we get. And so essentially, all these different situations, so I guess you would agree that graduating, studying, and dropping studies are quite different, and they're annotated as an education frame. And again, I would argue that this type of representation is again not terribly useful for answering questions. And I think this is really not a side note. So I think it's in general, we use semantic representation from the corpora which in principle are not good in many applications. So they're not good in general for reasoning. And we tend, in the semantic parsing community, we tend to be obsessed with the semantic parsing task in itself, but we often don't care if these representations are good for anything. And I think to make a progress and to actually show that our representations are relevant to application, to engineering tasks, we actually need to make a step forward and try to refine, to induce this representation to make them more useful in applications. And these challenges, both of these challenges, motivated a number of researchers to look into inducing frames. Here I mentioned unsupervised induction because that's where much of my current work lies, but we and many researchers now also move into semi-supervised direction. But let's stay for the moment in unsupervised. So it's motivated research in unsupervised models. And yes, there's been quite a bit of work in this direction. But I think there are a number of problems with models used in this area. So they're typically quite coarse. They use very restricted features. They make very strong independence assumptions. And then they have to basically rely to a large degree on syntactic representation. So they take syntax, they do a tiny bit of modification on top of this, and they think of this as semantics. And in this way, you can't really learn frames, say, which cross verb and noun boundaries. And then, of course, if you operate with these restricted models, you typically need to specialize them to different languages, and we will return to this point later on. And it to some degree defies the purpose of unsupervised learning if we need to anyway use data or use our lots of linguistic intuition and data engineering to tune it for individual language. And then again, what we also see is that type of semantic frames, semantic classes we induce in this way are often not very appropriate for reasoning. I think most of people in the audience understand why it's happening, right? So we often get antonyms put in the same cluster because you rely on distributional context, and they tend to be similar to antonyms. Okay, so what I would try to argue in this talk is that we can introduce more expressive models and also a bit different learning objectives, that's something not on the slide, to deal with, at least potentially deal with all these problems I have on the slide. And so that's the question how to do this. But getting back to the topic of our workshop, I think I'm a little still skeptical about changing distribution, natural distribution in the data, and basically screwing up priors in statistical models. I think the problem is largely with two things, partially with incentives, so that we as researchers tend to optimize our models for F1 score overall, and then it's of course hard to get improvement on this tail. Yeah. And another part of it, it's that our models are too coarse to dump in a way. So I think it was coming up in Antal's talk, or maybe it was not Antal's talk, not entirely sure. So there was mentioned that probabilities in a text changing. So the probability of observing the same entity again is much higher than observing it first time. But to me it suggests not that you shouldn't use probabilistic approach or not perform normalization, that you need to use some kind of smarter dynamic models, some kind of modeling on a document level. So I don't think we should say let's make it hard for probabilistic models. I think we should be more careful about ensuring that we work on the right probabilistic models, and you get some credit for working on these interesting probabilistic models. So that's my view on this. And in a way, in this project and what we're trying, we're hoping to go in this direction, because we're trying to use more expressive models, operating maybe on a document level and using somewhat different objectives. Okay, I think I'm a little actually slow. Okay, so I want to give you some conceptual idea of the framework we want to use. So the idea is quite simple, I would say. So say you have a text, or maybe a collection of texts, and so what you do, you leave out one fact from this text, and you're trying to predict this fact from the rest, but not directly from the text, but through some kind of intermediate semantic representation. But this semantic representation may be not observable. It's not something you know. You induce it specifically in such a way to make these predictions of left-out facts as simple, as easy as possible. So it serves as a kind of proxy for this, and you're trying to induce this to be useful. Okay, so you have here two parts. So we go from text to semantic representations, and we go from semantic representations to this prediction of left-out facts. So I call it encoding and reconstruction. So how do these components first on a conceptual level can look like? Okay, so first about reconstruction. So recall what we discussed about semantic representation. The semantic representation is, our semantic representation is in many ways similar to relational database. So we essentially predicting missing entities, missing facts in a relational database. And this is the problem which have been studied a lot in machine learning and statistical relational learning. So we can learn from the field a lot. So many recent models in this field, and not so recent ones, rely on factorization models. So tensor factorization, coupled matrix factorization, or recently more deep learning methods. So that's what we can try to use. And so what about going from text to semantic representations? So that's essentially parsing. And we have invested a lot of time in figuring out how to build parsers, how to get effective algorithms. But we typically did it in a supervised way. But now we can try to do this integrating in unsupervised induction. So now the question is, how do we estimate these two components together, this encoder and reconstruction? Conceptually, it seems simple, right? We have this kind of Lego, but of course, in practice, things are quite a bit more complicated. Okay, so this is a hand-waved slide, but I want to give you a little bit of intuition for why I believe this framework is promising. So if we're trying to predict missing fact, if we leave out a fact and trying to predict missing fact, we are not going to assign dropping studies and graduating and studying to the same semantic frame, because they're correlated with the different sets of events, they entail different events, so we should be able to disentangle them. So that should enforce our representations to be useful for reasoning. And as you will see, this kind of objective is also at least conceptually easy to optimize. Okay, so and then if we do this, in principle, we should get this first answer right away. But recall, we are not only learning the semantic parser, we learn also some kind of inference model as well. So if, say, we now have a question, where did he live? And knowing that studying, so the model should capture that studying in an institution located in the UK, it maybe implies living in the UK. So that's the principle of tensor factorization model should be capable of doing. And maybe even if we have enough data and it's not too noisy, and that studying piano maybe gives you some chance to become a professional pianist, right? So that's hope that we can do this kind of reading between the lines. Okay, so now a specific example. So this specific example is quite a bit simpler than what we discussed so far. But say you have a sentence, you know where arguments are, you know where predicate is. So this is observable. So the tuple of arguments is observable, but what you want to induce roles, so the tuple of roles and the frame. And recall, for the moment we're discussing unsupervised induction. So basically these are unobservable. So unobservable, sorry, we are not inducing fancy names. We will induce some kind of indices, cluster IDs. And we can argue whether this is enough, whether this is a good idea, but I'm happy to discuss this. So how do we define our model, our objective for this task? Okay, so much of latent variable modeling, I would say all latent variable modeling is basically learning a representation which helps you to reconstruct the input. Oh yeah, it says 17 minutes, okay. Anyway, so what basically happening here, we make it explicit. So instead of using generative modeling, what we say, let's leave out one argument and try to predict roles and frames which make these tasks as simple as is possible. And in a way, the underlying assumption that what we will get are semantic roles and frames, and I think it's quite a reasonable assumption because roles and frames are supposed to capture essence of the situation, and that's what we are trying to enforce by this objective, so that roles and frames and also arguments encode the essence of the situation. This model doesn't even have access to argument order and to syntax. Okay, so but here you can ask where do we have rich features. So actually, in the previous slide, it looked like we tried on our training set to search through the space of potential roles and frames, which makes this inference as easy as possible. But instead, what we are doing, we at the same time learning semantic parser, semantic role frame labeler. And this is, so we have now two models which we estimate jointly, the model which predicts roles and frames, and the model which fills in missing arguments relying on roles and frames. Okay, so I think I'm going to skip this slide, but I wanted to say that inspiration is coming from the neural world, and just to give you a bit of flavor of the model. So for encoding part, we use a structured linear model. So you can think of something like a conditional random field if you like, but or classifiers, or maybe something more complex. And here we use a tensor factorization model. So how this tensor factorization model looks? So we use similar ideas of kind of embeddings. So what we learn embeddings of arguments. So this vector u for an argument encodes its semantic properties. You can initialize it with the word embeddings, but you can just learn in optimizing our objective. And so what you want to encode to see that, say, demonstrators and protesters end up being similar when they're long, because they're substitutable, essentially, when filling up arguments. Now we also have, for every role in a frame, you have a matrix. So when you multiply this vector U with this matrix, you get some expectations of what other arguments could be. So if you know that agent is a police, so agent of assault frame, so we have embedding of police, we multiplied by representation of agent in the frame assault. We know that patients could be demonstrators of criminals, and this kind of belief which is propagated, and instruments can be, for example, batons, guns, or water cannons, maybe. Okay, so now we have a probabilistic model, so this signal is coming from observable arguments, so with sum it's additive for observable arguments, and we essentially construct the similar computation for potential arguments U in set, and you check if it matches these expectations, and it gives us this probability distribution of a potential feeders. But then you can look into other factorization models as well. Okay, so that was factorization part, and what is nice is that I don't really need to spend much time on frame semantic parsing part, because I think that's the beauty of this, that we can actually plug in existing semantic parsers, existing feature-rich models here in induce unsupervised estimation. But the only constraint is that we should be able to compute posteriors for frame latent variables and role latent variables, and also compute gradients of these posteriors. Okay, so how do we optimize them jointly? So if we would observe roles and frames, we could formulate something like a likelihood objective, or really what's called in machine learning pseudo-likelihood. So we predict argument, given other argument and roles and frames, and you wouldn't have Q and wouldn't have summation. But since we don't know roles and frames, we have to marginalize roles and frames out, and we use our Q model for this, and we estimate both parameters of Q and P at the same time. Here I will keep it short. There are few complications in principle with this approach. In principle, that's a reasonable objective, so we can just take gradients and try to optimize this. But it leads to very picky posterior distribution, so this is not very stable. So what we add regularization to keep these predictions of roles and frames relatively flat. And this is actually, we initially came up with this as a kind of heuristic way to regularize models. But what you would see is that we have this entropy term, this entropy, so we want it flat, so it's natural to use entropy. And we have something like expectation term, so expectation of this log probability under Q. And if you are familiar with, say, variational inference in machine learning, you will see that actually gives you low variational bound on likelihood, so it's quite meaningful objective. Okay, so let me basically, empirical relations, and I think I have only time to say that, and basically it works very well. But in principle, what we compare to generative and clustering approaches on role induction tasks. So where we induce only roles and frames as a predicate itself. And what is especially interesting, and maybe relevant to this workshop as well, that that what we see happening that our models, I mean, it's interesting, but also at the same time a little bit depressing, because previous unsupervised techniques used a lot, or at least some prior knowledge about the language. In say our non-parametric Bayesian models we used in the past. But here we kind of put together specifically on purpose something really agnostic to linguistic knowledge. So it's some kind of like kitchen sink semantic role labeling model together with very basic factorization. And we get results, I wouldn't say better, but on par with best approaches on English. And then what is interesting, when we move to German, we see the same picture. So whereas in the previous work, there had to be a modification to the model to get unsupervised model to work reasonably well on German. We apply the same model, and think even hyperparameters were the same and get the same difference. So similar story is for relational induction. So, but let me conclude. So I introduced a new framework. We're just starting to work on this thanks to funding we obtained. But I believe that it holds a promise to estimate expressive models while exploiting unlabeled data effectively. And I think this is actually the way to deal with tail. But of course, our problem is that improvements on a tail, unless we craft evaluation task in a good way, will not show up that much in a F1 score. So I think we really need to think of tasks where we will have incentive, or other people as well will have incentives to look in a longer tail. But I believe that still one problem why we are not doing too well, because very coarse model typically get a decent performance on a model in the head. So we know this, for example, for textual entailment tasks, that some kind of lexical overlap models perform quite well, and then it's very hard to get improvements, and then you need to do more analysis on which individual components you get in improvements, and many people don't go beyond this. Anyway, so this framework is extendable in many different ways. Even so far what we observed, which was a little depressing, that linguistic constraints appeared not necessary, but I think it's more telling us about other models than about our techniques. So previous techniques maybe we are not that good. It's not like ours is so painful. Yeah. So we need just figure out how to integrate linguistic knowledge. We look at semi-supervised learning, and in general also tight integration with knowledge bases and specifically learning for inference. Okay, thank you very much.
We have sort of been going into the discussion time already. Maybe we have time for 1 or 2 short questions, and maybe Stefan, you want to come and set up your laptop? Thanks. Yes?
So, do you think that if you look at the very large knowledge bases that we have now, like the linked open data graphs and the knowledge vaults and so on, do you think that the frequent patterns there, so there are some patterns in those knowledge bases which are more frequent than others.
Right.
Do you think that the frequency of those patterns could be good priors for learning your semantic frames?
I think you should be a bit smart about this, because of course annotation, so say in a freebase there is a bias of what people think are important relations, right? And this is not the same as frequency in the data, and I think you shouldn't really say, okay, the prior from this data should be really used as a prior. You should think of some kind of a more intricate interface, like multitask learning between them. And so what we want to go into, and we kind of go into, is trying to supplement the knowledge base, induce new frames, refine existing frames. It's especially relevant to FrameNet, because I think many knowledge bases were already designed to some degree with inference in mind, whereas many of semantic representations we have were designed to match linguistic theories rather than engineering.
Yes, but you're explaining how a knowledge base could be the output of this process, whereas I was suggesting that the knowledge base could be the input of
Yeah, but it's in some sense an input and output if we refine it, right? So that we correct, and so we can use for these relations as a prior, but we shouldn't believe that there are no other relations, for example, right? So so that I'm just saying that we need to do this in a more flexible way.
Short question.
Short? I don't have a short question. Okay, I'll try to make it short then. So, did you observe in running, in building systems and analyzing the data that there are effects of that the system just completely goes to the wrong direction because of, for instance, a head phenomenon, which is very dominant in there, but has a certain ambiguity, and it's pushing the data in the wrong direction. So,
yeah,
which could happen with, for instance, with word embeddings. I mean, it could be highly ambiguous, but
yeah, the quick answer is we do, right? And we actually in some other work where we looked at something like multi-sense, multilingual word embeddings, we actually observed that inducing them, assuming that you have senses, kind of explicitly modeling senses, helps to in the end tasks.
Okay, you
And
resolve it in the at the input side.
well, exactly,
Yeah.
essentially.
That's the semi-supervised
Yeah.
part also.
Yeah, that's, no, I mean, in this way we're not resolving it in an input set, we're kind of jointly modeling, okay, there is some distribution of senses which might be skewed, right? So we're not saying it should be balanced. So I think often you can design models in such a way that they would capture something which is not very frequent as long as the model is expressive enough and as long as you are not pushing it to have uniform distributions everywhere, right? And this is not always actually so simple. But we do have problems with this subject. It's not entirely success story, right? So
yeah, sure.
Just for 25 minutes I
of course,
attempt to...
No, if it would be only a success story, then there was no need for this one.
I'm really